All right, welcome. Today we're going to dive into what is, no joke, one of the most powerful and elegant ideas in all of mathematics. It's drawn straight from Chapter 8 of the legendary textbook Vector Calculus by Marsden and Trumba. We're talking about the great integral theorems. But look, this isn't just going to be a dry explanation of equations. This is about a single, absolutely beautiful idea that describes how the world works.
So, to really get our heads around this, let's start with a question. Imagine you're a scientist. How in the world could you measure the total swirling energy inside a massive hurricane? I mean, you can't fly through every single point, right? But what if I told you you could get that exact answer just by measuring the wind as you fly around its outermost edge? It sounds impossible, but this is exactly the kind of profound problem these theorems solve. And the key to that hurricane problem and so much more actually starts with something you already know. It's this incredible thread that connects your very first calculus class to some of the biggest theories in physics. Okay, let's get into it. Remember this one? The fundamental theorem of calculus. It tells us something truly amazing, that all the change happening inside an entire interval, you can figure that out completely just by looking at what's going on at its two endpoints, its boundaries. This simple idea, this is the seed for everything we're about to talk about.
A line is pretty simple, right? It's one-dimensional. Its boundary is just 2 points. But what happens when we level up? What's the boundary of a 2D area, like a piece of paper? Well, it's a closed loop. And the boundary of a 3D volume, like a ball, it's a whole 2D surface. So how does this whole inside versus boundary idea work then?
Well, our first big step up comes in 2 dimensions, and the answer is a beautiful result called Green's theorem. This is the first major generalization of that fundamental idea.
So what Green's theorem says is that if you could add up all the microscopic bits of rotation, what mathematicians call the curl, at every single point inside a flat region, that grand total is exactly equal to the total flow or circulation you'd measure just by traveling along its boundary curve. It's amazing. The stuff on the inside is perfectly mirrored by the stuff on the edge. And this image of a whirlpool, it gives you the perfect intuition for what curl is. Just imagine all the tiny, spinning water molecules inside that circle. Green's theorem tells us that if you could add up all of that spinning, the total would tell you exactly how fast the water is flowing right at the edge of the drain. Okay, so we've got 2D covered, but the world isn't flat, right? What about surfaces that are curved, like a sail or maybe a parachute just hanging out in 3D space? For that, we've got to level up again. And this is Stokes Theorem. You can really think of it as Green's theorem in 3D. It says basically the same thing, but for a curved surface. The total amount of swirl or curl that passes through the surface, kind of like the total rotation flowing through a net, is equal to the circulation along its boundary loop. Same idea, just curvier. And here's a fantastic application: making planes fly. Stokes' theorem is absolutely fundamental to understanding lift. It lets engineers connect the circulation of air flowing around the edge of an airplane wing to the pressure differences across the entire wing's surface. And that's the magic trick, you see. It turns a really complex surface problem into a much, much simpler line problem. Okay, so we've done a line, a flat area, a curved surface. There's only one place left to go, right? A full 3-dimensional volume. And this brings us to our final epic theorem. This is Gauss's theorem, sometimes called the divergence theorem. Now notice the language has changed. We're not talking about swirl anymore. Now we're talking about divergence. Basically, how much a field is spreading out from a point, like a source. And Gauss's theorem says that if you add up all the little sources inside a volume, it will exactly equal the total outward flow or flux through its boundary surface. This diagram from the book shows the idea perfectly. If you've got some amount of stuff inside this volume W, the only way that amount can change is if stuff flows across its boundary surface, which is J here. It's just a fundamental law of conservation. If more flows out than in, the total amount inside has to drop. It makes perfect sense. And think about the sun. It's this giant volume producing an unbelievable amount of energy. Well, Gauss's theorem tells us something incredible. We don't have to go inside the sun to figure out its total power output. Nope, we can just draw an imaginary sphere around it, measure the total flow of energy passing through that surface, and that's it. What happens on the inside is revealed on the boundary. So let's pause for a second. We have Green's, Stokes' theorem, and Gauss's theorem. On the surface, they seem different. They use different math, curl, divergence, and they apply to different dimensions.
But if you look closely, they all share that exact same DNA. What happens inside a thing is totally encoded on its boundary. Now, in math, when you see a pattern that strong, it's usually a huge sign that there's something deeper going on, a more fundamental structure that connects everything. And in this case, oh yeah, there is.
So here's the crucial point. All of these theorems are really just different views, different shadows of a single, much more powerful idea. There's a mathematical framework called differential forms, and in that language, all of these theorems become one. I'm serious. The fundamental theorem, Green's, Stokes, Gauss's, they all collapse into a single, unbelievably elegant statement. Basically, the integral of a thing's derivative over a region is equal to the integral of the thing itself over that region's boundary. One equation to rule them all.
Now, that is super elegant, but you might be thinking, okay, is this just a cool math trick? And the answer is absolutely not. This single unifying idea is the operational backbone for enormous areas of science and engineering. This isn't just theory. This is the very language used to write the laws of electromagnetism. It's how we design turbines by understanding fluid flow. It's how we model heat transfer. It's how we calculate gravitational fields. It is woven right into the fabric of modern physics. Every single time you use an electric motor, you're looking at these theorems in action. Faraday's law of induction, one of Maxwell's legendary equations, is literally just Stokes' theorem in a different disguise. It connects the changing magnetic flux through a surface to the electric field created around its boundary. And every time engineers design a dam or a submarine or an airplane wing, they are using these principles. The fundamental equations of fluid motion, the ones that tell us how water and air actually behave, are built directly on the concepts of divergence and curl.
And for a truly mind-bending example, these principles explain something that seems completely impossible: how an astronaut can turn around in space without pushing off of anything. By moving their arms in a cycle, they trace out a sort of surface with their motion. The math of Stokes' theorem actually shows that this internal motion can create a net rotation of their entire body, a change on their own boundary.
And that really brings us to the final thought here. This incredibly powerful idea that you can understand the interior by looking at its boundary, it's like a new lens for seeing the world. From a hurricane to an astronaut to the sun itself, some of the deepest truths are written right there on the edge. It makes you wonder, right? What else could we understand if we just knew where to look for the boundary?